Hello again, this is Galen Pickett, Cal State Long Beach, and this is Physics 151. So today I want to talk to you about Section 10, Chapter 3, and Chapter 4 in Chapter 2. This is about the iterative model of capturing motion and this philosophical idea of mechanical determinism. So the question is, if I know the only information I have about some system, some object, is where it begins at some initial time, how fast it's going, so I know where it is and where it's going, and if I know what the forces are at all later times, can I tell you exactly where the particle winds up? And the answer to that is yes, and there's an approximate scheme for doing this. So the inputs is R initial, V initial, and whatever the force is. So the way we will get an estimate for where the object is, where it's going, and what the force is, the output we need is where does it wind up, how fast is it going, and once we know about those two things, we can figure out what the force is again. Now I'm going to work out an example where the force doesn't change in time. We could write this as the initial force and the final force. Put it in quotes because I'm going to keep the force a constant for this illustration. And we've already done this. This is the momentum principle, average velocity, position update chain of reasoning that takes me from the initial to the final. I'm just going to do it time and time again. So here's what it looks like geometrically. Here is the initial position of the object. Now, under the hypothesis that the force is equal to 0, so this is just a special case of this. If the force is equal to 0 and V initial times delta t is this displacement. So there's my initial position. The initial delta t takes me from my initial to my final. There's where the R final is going to be. So I would get R final is equal to R initial plus V delta t. And that's something you know as the position update idea. And in fact, it's V final. The velocity didn't change because the force was 0. And now, once I know what the R final is, I can rename this new R final as the new R initial. And since the force didn't change, the V final is the same as what the V initial was, and the force is still 0. So, from my final position, I call this the new initial, and I add the same displacement in the next delta t, which takes me to my next R final, and to my next one, etc. So what I get is the force is equal to 0. If I follow this scheme, I get a set of data that takes me from one spot to the next. I'm just moving at the constant velocity, constant direction, constant displacements. This is F is equal to 0, no interaction motion. And that's something we talked about in Chapter 1. Now if there is an interaction, let's see what that might look like. So again, I'll give myself my initial position is right there, as some dot. And I'll give myself some interesting initial velocity. So let's say that my V initial delta t looks like so. So if there were no force, I would wind up exactly here. But there is a force, so we'll use now the momentum principle to figure out what the new velocity is going to be. So I've got m v final is equal to m v initial plus, and I'll put this in red, f delta t. Now if I divide, so that's just the momentum principle in its update form, as we've used it before. If I divide both sides of this by the mass, I get that the final velocity is equal to the initial velocity plus, I'll put it in red here, F delta t over m. So if I knew what the force was, the delta t and the m, I could tell you by how much the velocity is going to change. So I'm going to let the force be this little red vector here. This is a vector, it's a displacement. It tells me what delta t times F delta t over m is. That is this change in velocity, that velocity, times how much time goes by from one time step to the next. So this blue arrow is where I would go if there's no force. I've got to change it by adding this little red arrow to it. And that is the real final velocity. So here's the new R final. Then I use R final is equal to R initial plus V final delta t. And now I use this state as my new initial state. So that's my initial position, and this, the velocity which took me from my initial to my final, that's my new guess for what the initial velocity is. So if there were no force, I would wind up exactly here. But there is a force, and the force is going to cause me to have a different velocity. So I've just added in that same velocity here. So now my position is here. So instead of going in a straight line, you can see that there's some interaction here. You need 3 dots to see an interaction, and there's the first time we can see it. Here is what the final velocity is, so that's going to be what the new initial velocity is. I have to add this red arrow to it, and I get right there. So there is now my new final velocity. That's my guess for what the initial velocity is going to be. This vector is the same as that one, but I have to add this little red vector to it. So I wind up here. And I think you can see that we've got this trajectory now that looks exactly like one of these parabolic trajectories that you studied in that first tracker experiment that we have done in this chain of reasoning here, the momentum principle, average velocity, position update idea. Doing that gives us exactly this kind of motion. And the inputs here, the only thing I needed to tell you was the initial velocity and this is, or the initial position and this initial velocity. From those two pieces of information, every other dot, every other notation that I made was set. And that gives rise to this idea of mechanical determinism. This is a philosophical idea. It says that the entire world, everything in the world, is determined by the mechanics of the physics in it. And its most disturbing form was stated in the 19th century. Suppose I knew all of the positions of every object in the universe, all of the atoms. I knew where every atom was at one particular time. And I knew what all of their velocities were, all their momentum. And I knew what all the interactions were. If I knew all those things, then all of the positions in the future would be completely known. I would be able to predict the behavior of any mechanical system, including how people move and speak and talk and walk. There's no freedom. There's no freedom, there's no free will in this kind of philosophy, and that is the problem that people in the 19th century were very concerned about. And to my mind, it's still not a resolved problem. However, you have taken advantage of this mechanical determinism thing to do video game physics. After all, you only have a very few number of controls on a video game, and once you've done your controls, you want the behavior of the game to be exactly what your controls said. Here's an example of it that you've played before, undoubtedly. This little bird starts in this slingshot, this U slingshot. So the initial position of the bird is determined by the game. And you get to determine the initial velocity. So you can pick the direction of the velocity and what its magnitude is going to be. So it is a two-dimensional vector. There's 2 inputs you give. So I'm going to give it some input and we'll see what happens. From that point forward, I do not control what happens in the game. The game controls what happens in the game. And if you see here, these dots show exactly the breadcrumb trail that we have developed here. So the game actually gives you the frame-by-frame trajectory of the bird as it was flying. I'll just let you enjoy my 3 stars one last time before we move on.